afternoon, everyone. We're going to go ahead, just in case it takes me a little bit longer to explain a couple stuff, because I want to be as thorough as possible. This is very complex data that we're going to show, and we want you to understand everything for sure. First, I want to thank Dr. Acevedo here for giving us this opportunity and her team. So without her, we wouldn't be here. Without she spotting us a couple months ago, we definitely wouldn't be here. And thank you to the people that has joined in online. This is an amazing opportunity, and I'm really happy to be here presenting this and sharing all the data that we have produced in Ronawk and that our collaborators have produced all around the world and all around the United States. This presentation was entitled as Generating Tissue-Mimetic Environments to Accelerate the Production of the Next Generation Biologics. And the video that is playing right now is just an example of the microenvironment that the BioBlock universe actually allows you to create. And this is an AXR confocal image. And just to clarify, this is just one pore of one section of our product. Just imagine if that beautiful image is just only like less than 1% of what our entire product is, what else is in that environment in general. So hopefully this video and this brief introduction is making you question of what is a BioBlock and what is our product. So BioBlock is a 3D printed hydrogel that is composed of three main characteristics. It's microstructure, it looks like a puzzle piece, and it will allow you for a more controllable properties and that will mimic tissue mechanics. What that means is that we have at Ronawk the capabilities of manipulate that hydrogel so it mimics the mechanics of your tissue of interest. Not only that, because of how we have developed this and its microstructure being able of a very modular system, you can actually eliminate your need for self-culturing, especially if you're doing a lot of 2D tissue culture. It also reduces your lab waste because you're confined to probably a plate. You're also using way less media because you only have to cover that. And this microstructure, which is our third characteristic here, allows for a pore of network of pores that allows for transport of nutrients, gas, and of course cells, and that's what you're seeing here. And that microstructure allows for the formation of very complex structures that mimics what you're seeing in a in vivo model or your patient in this case. As I mentioned, the porous microstructures is equal for us as a mass transport of nutrients, cells, and gas. So in this image, the first one here, A, this is our BioBlock, and it's placed actually in a chem wipe, and we had added 1 ml of quote-unquote media, and you can see that within 2 seconds that media is running through our pore channels and our pore network, and is getting absorbed by that chem wipe out here. And the same can be said if that media had cells, the same will have happened. You can see here, this is the exterior, so the top of that block, and we can see how the cells have penetrated the block and have been organizing the cells inside those pores to form their structures. And in terms of gas, this was a collaboration with O2M, and they ran a gas distribution for our block, and we can see that it's pretty uniform all across the sea of that block. You might be questioning, so how big is this block? It's actually 1 centimeter cube. It's quite big for a three-dimensional matrix to grow. And as I mentioned in the first slide, we can modulate that mechanical stimuli that the block, the matrix, will give you. In this case, our most popular block, which is the X block, is being targeted to be 3 kilopascals. That will emulate adipose tissue, and that is due to our interest internally in mesenchymal stem cells, specifically adipose-derived mesenchymal stem cells. And that is very important because if you see this image right here, depending on the stimuli that you're giving your cell is how that cell is going to behave. And if you're planning on developing new therapies, a cell that doesn't behave that it does naturally, it will give you false false positive data there. So this is just an example of mesenchymal cells culture in different stiffnesses and how they show their differentiation in terms of their osteogenic potential. And we can see that the more stiff they are, the more they behave like osteoblasts and osteoblasts, which it was their main goal there. So we have been talking a lot about mimicking the environments, the natural environments and all that. And I just want to reiterate that all culture systems are valid for a reason. And our system doesn't invalidate your research at all. It just gives you an opportunity to explore a new biology that you probably hadn't thought of or haven't had the opportunity to. With that said, there are challenges with each one of the culture systems that are available right now commercially and just in the academic settings. 2D is a great way. Without 2D, we would have never understood cell biology 100 years ago. So, but the problems and challenges that 2D brings is we have only one mechanic, it's either plastic or glass. And again, cells do not behave normally there. Normally, you have very issues in translating your research there, and of course, in nature, plastic or glass doesn't exist. If you think of yourself, there's no surface in your body that actually will emulate glass or plastic there. Other tissue culture systems like organoids and spheroids are great, and I think that the research that we have come the last 10 years with the introduction of organoids and spheroids and the need for three-dimensionality in culture systems, it has been amazing because we were able to see more in vivo-like structures, those cell-to-cell interactions, the importance of the microenvironment that the cells form there, the importance of matrices, why the cells are producing so much ECM when they're developing new organs and stuff like that. However, as you may have encountered, organoids and spheroids are very hard to scale up, they're very expensive, they often don't propagate, and they have a huge issue with mass transport, especially on gas and nutrients, ended up developing those necrotic cores that then make you question, is the data I'm getting here real or what's going on? And of course, and you guys have an amazing facility with animal models here. Not everyone has animal models accessible for them, but of course the challenges there are they're very expensive, and there's a lot of ethical issues. I'm pretty sure you guys have encountered someone that doesn't agree with your research because you're using animal models. So our product goes right in between 3D culture systems and animal models because it allows you for mimicking that natural environment that the animal model offers you, while also being able to scale it. It's really easy to use and develops that mimicking tissue and potentially for those development of new therapies there. Now, I don't want to say that our product is perfect because it's not. Has several challenges, and that's where you guys play a role. There's so much we can do as a company, but with collaborators in academia and industry and many other settings, we can actually expand more on how to use this product for different research areas, but also to develop new methods to understand the biology that we're seeing in the product. So for today's objective of this presentation is for me to communicate the capabilities of Ronack's BioBlock to unify research areas by facilitating collaborations for the advancements of new therapies. In this case, one puzzle piece at a time. With that said, just a disclosure here, I am employed by Ronawk. A lot of the data that I'm going to present here is either hasn't been published or it does contain some sort of proprietary information that I might not be able to completely disclose with you. But we are free to actually meet after this talk or tomorrow to talk more about your research and how our product can help you advance your research. So these are some of the research areas that I'm planning on talking today. We have neuroscience, cancer research, iPSCs research, cell biology, wound healing, and the next one will be whatever you fit. With neuroscience, if you guys were at Dr. Diana Acevedo's talk, we'll talk about how she used our product to develop a tumor microenvironment using neuroblastoma cells and Schwann cells. And some of the things that maybe she didn't mention there is that this is an AXR confocal imaging. And this C-stack is showing only 1/4 of the entire block at approximately a 1% of the entire block in terms of the C. So this is just the penetration that our current microscope has. So you can see that the cells are actually interacting with each other inside of those pores. And we did some more sectioning of that, and we can see that even in the center of that block, the cells are still interacting, forming their own little niches. If tumor microenvironment is not your thing, but you have progenitor neuronal cells here, we have also worked with collaborators that does this. Their goal was to, as a proof of concept, know if their cells will grow in our matrix. And what they saw was they did a culture of, I believe was 14 days. We will see here. And you can see that by day 7, there is growth of those cells in the different areas. So these dark spots right here are what we call the pores. By day 9, those pores, which are even more visible here, are being filled with those cells, and the formation of complex networks and complex structures is starting to happen. And by day 13, you can see those very delimited neuronal network connections that they were forming. Unfortunately for this, they didn't took this further. But we're continuously working with them to develop a better matrix for them. They want something smaller, not as large as what we currently have. But this cell behavior that we're observing here, they have never observed that before, especially in their 2D environment that they were working with. Another area will be cancer research. For this area here in this collaborator, they were interested in developing a drug-resistant cell line for the development of new therapeutics in their research. And this set of data is going to be divided into two. We're going to show you some images here, and then we're going to dive into the more developing of that persistent cell line. But just as a note, the days of culture here, the cells have been exposed to the drug from the beginning, from being seeded into the blocks. And as just an anatomy of our block, here is the center pore. That pore goes top to bottom, and it's the only pore that goes top to bottom, while you can see the other pores surrounding that one, and those will they will be like little stairs inside of the pore. You can get to different levels of the block. And what we can see is by day 2, there's some like shadowings of cells there, but definitely by day 6, the pores are even less visible, and by day 7, you can barely differentiate what was the center pore from what is your normal pore, because the cells are populating all that area there, and it's difficult to differentiate. And then by day 8, you can see the big cell populations inside of those pores. So she took this culture for up to 45 days. That's something that we're gonna mention, I believe, in the next section of data I'm gonna present. And while dosing the cells with the drug of interest, what we saw is for the cells grown in 3D, we saw an increase in their GI50. So their GI50, they define this as the concentration at which a drug kills, in layman's terms, half of the population of the cells. And just so it's a little bit more digestible here, you can see that the GI50 for the cells that are grown in 2D actually decreases over time, while in the cells grown in 3D, it goes increasing until it plateaus. So right now, what we're doing with them is taking this paradigm and expanding it to do different dosages over time, increasing that dosage so we can see a more exponential increase of that GI50 so they can develop that resistant cell line. And you might be questioning, why is this important? For developing of a resistant cell line, especially in a 2D culture system, it takes 1 to 3 years. This is just happening in 45 days. So this is very impressive. For the next research area that I want to focus and highlight is the iPSCs research. Interesting enough, we had 3 different collaborators contact us and say, hey, we want to grow iPSCs in your product. And we get a sample. And we went ahead, we sent some samples there, and we grew some of these cells for different periods of time. And interesting enough, all 3 collaborators saw exactly the same thing. And that is that by day 1, the cells started forming aggregates inside of the pores and surrounding the blocks. What does that mean? It means that our matrix is promoting the cell aggregation of iPSCs, and this is not only happening with 1 donor, but with 3 different donors. So it's very consistent there. And most importantly, by day 4 to day 7, these aggregates get actually expelled from the block, and you can actually collect them or see them with your own eyes, so you don't even need a microscope here. So this was very interesting, because we defined this as complex structure formation that was going on, and this is collaborator 1. For collaborator 2, they sent us this image and they were like, I don't know what's going on here. And interesting enough, you can see the big aggregates that are getting actually out of the cell. But if you see this shadow right here, those are aggregates that are being formed inside of the block that are not getting out yet. So this is just on iPSCs production. Just imagine how many cells are actually being produced in the matrix. Then we had collaborator 3, which took this even further. Right now, she's been culturing iPSCs for over 60 days. It's the same block that we gave her 2 months ago. So you have been able to grow iPSC for 60 days from the original bio. Please let me know. I want to see them. But you can see here that for 1 day, again, you have that aggregate formation. By 4 days, those aggregates are like forming in all the pores, and they're getting bigger by the time. By day 10 and day 14, those aggregates were getting expelled out of that block, and you can actually see them right here, hopefully. Those aggregates that got expelled, she collected them and performed qPCR on them. And what she saw was a 2-fold increase in stem markers for the cells that came out of the aggregates from the block. This is pretty impressive. Not only are you producing a massive amount of iPSCs from the blocks, but you're also producing a massive amount that is retaining those stem markers. That is very hard to keep. In that same line of retaining stem markers, retaining phenotype, cell research or cell biology research that I'm going to discuss here, we're going to talk about 2 things. The reduction of senescence, which is the cells just getting old, and the retainment of cell phenotype. So this was done internally by Ronawk scientists, specifically Dr. Hodge. Our interest in, and I can click this back, our interest in Ronawk is for wound healing therapies and regenerative research in general. Dr. Hodge focused on the growth of adipose-derived stem cells, which are a type of mesenchymal stem cells, and he was interested, and he's still interested in the way that we can use them, especially their secretome, for the development of new therapies for wound healing. Something that happens, and especially if you guys have worked with cultures here, especially primary cultures, is that once you get to a certain number of passages, that cell is useless. You either don't have the phenotype that you started with, and in this case, you start increasing their senescence. And what we did here was that cells will grow in 2D flask or a plate, and in 3D, in this case, in our bioblock, for a series of days. For this experiment, it was 42 days, which equals to around 10 passages of the 2D counterpart control. And what we saw is that when time goes by, especially for the 2D, we start seeing an increase on the senescent cells that are labeled here on green. And by passage 10 or 42 consecutive days being cultured in the bioblock, we can see that the senescence population in the 2D is really high. While if you see the 3D here, there is minimum to no senescent cells. And this is just a graph of the inverse. The non-senescent cells, we see that we keep at around 95% of non-senescent cells for the bioblocks, while, for the cells being cultured in a 2D flask, we see a decrease in those non-senescent cells, aka there's an increase in the senescence population. We then took this even further and say, okay, yes, 2D culture affects the senescence in the sense that it's increasing the senescence, but there are many other ways that we can culture cells, especially MSCs. So we tried to culture MSCs in the 2D control, our bioblock. We also culture them in low attachment, round bottom plates to create spheroids, and we also created spheroids with matrigel in them. And what we saw is that by week 4, we see very minimal increase in senescence population in the cells growing the bioblocks. For the 2D, we saw that same increase as previously for the senescence population. But interesting enough, in the cells grown in the matrigel, it is a very significant increase in population even at week 1. And for those of the cells grown in sphere-like structures, it's an even higher senescence population there. What this means is that even though you're using other 3D matrices and 3D formats to grow your cells, you might be losing the potential of your cells for retaining their phenotype and even retaining their stemness in general. Talking about retainment of phenotype here, he also performed different phenotype markers. He confirmed this data that I'm going to present here with genetic markers for the specific phenotype. And what he saw is that by culturing cells in the bioblock in this 3D format, even after 42 days of continuous culturing, the cells keep their phenotype markers. In this case, it's the stem-like markers. In the next section, so after he grew the cells in the different formats, 2D, matrigel, spheroids, and the bioblock, he actually tested for the potential of differentiation. So we know that the MSCs are able to differentiate in different cell lines. In this case, he was interested in osteogenic differentiation, adipogenic differentiation, and chondrogenic differentiation. And what we can see here is in this data specifically, which was done prior to challenging the cells for differentiation, is that the bioblock cells exhibit a greater potential to differentiate into their multi-lineage potential. And that was confirmed once he challenged the cells for differentiation. And we can see here that the consistency of that differentiation for the cells grown in the bioblock is way higher than those in the other formats there. We have it's more homogeneous, that population of cells that were differentiated. So we're retaining that phenotype. We are delaying that senescence there, and we're keeping the potential of those cells to actually do what we wanted them to do, in this case of the MSCs, to differentiate in the, to the specific lineages, but just if you're working with iPSCs, we will keep retaining their ability to differentiate also there. And the last research area that I want to mention here, because we have been collecting lots and lots of data, is in the wound healing research aspect. I know I've been talking a lot about mesenchymal stem cells, and you probably know a lot about them, but in this area of research, I want to mainly focus on their secretory abilities. So we're very interested in the production of those cells, what they produce, how can that product be used for new therapies in wound healing, specifically in the extracellular vesicles that they actually produce. And what we saw while growing MSCs in the bioblocks is an increase in the secretion of soluble proteins, which I didn't mention, but I showed before, is related to the secretome of MSCs. The secretion and increase of antioxidants, and more specifically for our own interest is the increase in the secretion of EVs. And this increase is of a 5-fold. It can get up to 10-fold, which is amazing there. Once we saw that, what we then did, was that we wanted to assess the indirectly the measurement of the functional and quality of that secretome component. So what we did was we cultured cells, MSCs again, in the bioblock, and we also cultured the MSCs in a 2D environment, in this case a flask. We collected that media produced by those cells after a period of time, and then we centrifuged that media and just isolated those secretome proteins there, and then we treated keratinocytes with that media and saw different things. So the first thing is the metabolic activity and their proliferation. We grow the keratinocytes for over 24 hours exposed to this media that contain the secretome from the MSCs, and we saw a significant increase in their metabolic activity as well as in their proliferation rate. We then took those keratinocytes, did a scratch assay, and then added the media that was collected from the bioblocks and from the 2D MSCs, and we saw an increase in their migration. So what we're seeing right now is an increase in the metabolic activity by the secretome of the cells culture in the bioblocks, and increase in their proliferation, again by the secretome produced in the bioblock, and an increase in the migratory activity by the secretome of the bioblock. Now, this is very interesting. I wish I could share more information. So what I'm going to say is keep in the look for our next paper that's going to take this even further, where you can actually modulate all those activities depending on how you code your bioblock for a specific area or a specific protein. So it's amazing the work that Dr. Hush has done with our product here. And these are just a sneak peek of the many research areas that we have been collaborating. We have many more here, and we expect to have even more. So if you're interested in the product and capabilities of the product, please let us know, because we're here to help. We're here to advance the research more than anything else. With that said, the takeaway message of this presentation, besides being able to communicate those capabilities to Unifying Research, is that the bioblock allows you to form tissue-mimetic environments. It allows to preserve the cell phenotypes. It delays the cell senescence. It increases the production of biologics. It encourages in vivo cell behavior, and it allows for cells to thrive in harsh environments. And all of this is possible because the cells are being cultured in an environment that mimics their native state. And with that said, I would like to acknowledge again Dr. Diana Acevedo. Without her, we wouldn't be here, but most importantly, the Ronawk team. With all the help that I get from our staff and all the hard work that our scientists have put into understanding what's going on in the block, none of this presentation would have been possible. So thank you so much, and we are open for questions.
I was curious how customizable these bioblocks are. So I think one thing that you mentioned is that can you modulate the rigidity of the matrigel, but are there other features that you can change?
So we can change the microstructure. So it doesn't have to be a puzzle piece shape. We can modulate the mechanics of it. The only thing that we cannot change is the microstructure. That is the uniqueness that allows for all of this to happen, for all the cells to thrive this much.
Are you talking about the actual pores?
Yes, we can change the size of the pore, so we can go bigger as to almost a millimeter to smaller 100 microns. Right now, our popular product is 300 micron pores. The second most popular is our 500 micron pores. That will depend, whenever we have a talk, we will talk about your cell size and all that, and depending on how big your cell is, we will deviate into which area, how big the pore you might need.
Do you have any interest in simulating gradients? So you talk about mass transfer, right? That's pretty cool. But is there any way to change, like make one side of the hydrogel less able to, like, less permissive to things?
Yeah.
Molecules.
So currently we offer 2 different types of polymers. We have a more synthetic polymer. That polymer, you will have to coat it with something for the cells to stick. So if you don't want your cells to stick to that one, but still migrate through it, you will be able to do it. And then we have a natural polymer where the cells actually stick to it. You can coat the block with whatever you want. So if you want a gradient of drugs, we can do that. You can do that. It's the modularity of it, because it's a puzzle piece. You can just put different concentrations of your whatever you're interested on that gradient in different blocks, and just put them all together and put one block that has the cells and see how they interact with all those different gradients. Unfortunately, I have to take all of those animations of potential essays that you can perform out of the presentation, but we have them, we can show them to you. But yes, that's something that can be done. If you wanted something more specific in the sense that you want a gradient of X protein inside of the block of the structure, that will be more of a customization type of product, and it will be a more in-depth conversation with Scott and our CTO, Heather Decker.
It seemed like you had some examples of where whatever cells you seed with were contained within the pores, but there were also instances where there was infiltration into the surrounding area? Okay, so
yeah.
that's...
So unfortunately, I cannot show you that data, but I can talk about it.
Yeah.
We have seen the cells actually forming what we call bridges. So from the protrusion, which is the outer part of the block, you can see bridges of cells going from one protrusion to the other, or in the intrusions, the cells actually covering the entire area. Now, is that just cells? I don't think so. I believe it's a mixture of cells and extracellular matrix. It's just that the cells know that there's space there that they cannot travel, so they're forming their own highways to actually access new areas of the block.
Thanks.
No problem. Any more questions?
So of the aggregates that you, in regards to that first, very nice presentation, thank you very much. Also, in the aggregates of the iPSCs that you saw blending on top of the block, as well as the ones that were embedded, did that investigator, and I don't know if you can talk about it, but did that investigator take those cells and have them differentiate to whatever cells they were looking at?
So currently, actually our third investigator tried to do some differentiation. Unfortunately, she faced with the problem of having expired products. So we're continuously working with her so she can get new products and everything to do the differentiation. She confirmed that the differentiation actually failed due because even her 2D failed also.
Thank you.
No problem. Any other questions from our online community? I don't hear anyone else, so thank you everyone, our online community here, and you guys are present. It was a pleasure to talk to you guys. It's going to be a even greater pleasure to actually dive into your guys' research and understand what you guys are doing and see how can we help you. Thank you so much, really.